Okay, so the sixth and the fifth study unit are very much related in terms of the concepts they bring about. And so six, the topic is network reference models and standards. And the following outcomes will be covered in this presentation. Explain the OSI reference model layers and their relationships to hardware and software. Explain the IEEE 8.0 networking model and related standards. Describe the purpose of a network protocol, the layers in TCP/IP architecture, and protocols in each IP layer. And lastly, explain IP configuration and subnetting. Okay, so in Unit 6, the focus was around this model called the OSI model, which stands for Open Systems Interconnection, right? And by looking at the OSI model, you'll be able to tell that it brings about some concepts from Unit 5. It involves a lot of protocols, right? So we say that the OSI reference model proposed by the International Organization of Standardization has become a key part of networking because it provides a common framework for developers and students of networking to work with and learn from. Okay, so it helps us to better understand how data is transmitted through a network. It's sent through several layers. And this International Organization for Standardization is actually it's actually a very broad organization in the sense that they define a lot of standards, not only just for networking purposes, but they also define standards for coding software, standards for engineering, construction, multiple industries. So there is a set of standards defining how data is sent, which is the OSI model, and standards for also transmission mediums, which is IEEE 802 standards, which we're going to talk about later on in the presentation. So the OSI model is not specific to any protocol suite and can be applied to most networking protocols. OSI model is a 7-layer organization of how data travels from one place to another place in a given network. Okay, so how do we then define a network? So we say it's a set of guidelines which define how this data is transmitted. Okay, and the most common protocol stack is TCP/IP. TCP, Transmission Control Protocol, and IP stands for Internet Protocol. Okay, and there's a wide variety of TCP/IP related protocols. So when you see TCP/IP, we refer to it as a protocol stack or a protocol suite because it's two separate protocols, but they are used together to transmit data, most importantly to the internet. Okay, so for now, don't worry about the layer names. If you're just looking at the protocols alone, you can see HTTP. It's a commonly used protocol on the internet, hypertext transfer protocol, okay, for rendering web pages and so forth. We have SMTP for email. We have FTP. We have POP3. So there's a wide variety of all of these protocols. And if you're looking at it at the application level, okay, so you as the end user using an application, you may interact directly or indirectly with these protocols. For example, if you are sitting in front of a web browser and you're browsing a website, you're interacting directly with HTTP because you are typing HTTP domain on the web browser to open up the web page. But protocols like SMTP for sending email and POP3 for receiving email, you don't really interact with those directly, but you use some sort of application to send and receive emails. Okay, same thing applies with DNS and DHCP, but I'll save those ones for later on in the presentation. Okay, then there's also TFTP and SNMP. Okay, so those SNMP, which is for messaging, it's messaging protocols. So so for now, if you're looking at protocols from the perspective of applications that we normally use, okay, we can see that there's a set of instructions or guidelines that govern how things are sent between the sender and the receiver. Okay, so when we break down the OSI model, we want to talk about the significance of all of the other corresponding protocols. So TCP versus UDP. These two are referred to as transport protocols. Why? Because they determine the method in which the data is actually sent from the source to the destination. It's like how are you going to get to town? Am I going to take a bus? Am I going to take a taxi? Okay, and if you outline the two, there's always pros and cons to both. Okay, if we're looking at TCP, TCP is not used alone. It is a protocol suite. Okay, it's used along with IP, which is Internet Protocol. So it keeps track of lost packets, make sure that the packets are resent, while UDP doesn't keep track of lost packets. So already, by looking at the first comparison between the two, you can tell that UDP is not as reliable as TCP. Okay, and the second one is adds sequence numbers to packets and reorders any packets that arrive in the wrong order. Doesn't care about packets arrival order. Okay, in actual fact, UDP doesn't even use packet exchange because it sends a chunk of data to the destination. It just sends it out there. It doesn't chop it up into packets, data packets. TCP is slower because of all the additional added additional functionality. UDP is faster because it lacks extra features. Okay, UDP is very straightforward. I am the source. What is the destination? Send the data and just hope that the particular destination is listening at the port that we are sending to. Okay, so that is a very unreliable way of sending data. However, it's very fast in the sense that it doesn't have to do all that additional chopping up data into packets, assigning headers, and so forth that you see in TCP. So also TCP requires more computer resources because the OS needs to keep track of ongoing communication sessions and manage them on a much deeper level. Okay, so it's very complex, reliable. There's this communication sessions, termination, and reassembling packets on the other end. As in contrast with UDP, requires less computer resources. Okay, so some examples that use TCP is websites, many computer games which gamers play online, where the person is playing with another person located somewhere else in the world. Those two computers need to exchange each other's IP addresses, so to keep the communication valid. So we tend to say that TCP is connection orientated because before the computers communicate, they acknowledge each other. Okay, they exchange information about each other. So you can see the list of those services that use TCP. In contrast, UDP, examples of programs and services that use UDP, DNS, IP telephony, DHCP, and sometimes other computer games may use UDP. Now, I tend to use the example of Skype. You are doing a call on Skype, and something like a video conferencing application would make use of UDP, because in terms of a video call, it doesn't really matter if you lose a couple of frames. Okay, yes, you're gonna start to if the network drops, you're gonna start to experience lags and stuff like that. But it doesn't really matter. It won't really damage anything. But if you are transmitting a document, transmitting a web page, and somewhere there is a break in communication and the network fails, then it means that that web page either won't be rendered at all or would be rendered partially. Okay, so that's the significant difference between the two. We tend to say UDP is good when there is no there's not much of a risk in terms of the data that's being transmitted. But if there's a high risk of loss, then TCP is favored. So an IP address is assigned to every computer and network device using TCP/IP for communications. IP addresses are used for two main purposes: identifying a network device and to identify the network which the device is connected to. So looking at an IP address for a computer or any node or any device, for it to be able to participate on a network, it needs to be assigned an IP address. Okay, and IP addresses are unique. Okay, no two computers can have the same IP address at the same time. The other thing you must know about IP addresses is that we lease them out. So today you may be connecting your phone to a network using a particular IP address which you don't assign yourself. It's assigned to you by a specific protocol, which we're going to talk about later, but an IP address is assigned to you. You connect to the network and you lease it for X amount of time. After the lease expires, you don't even see it happening, but you get assigned a new IP address. Okay, so when a device receives an IP packet, it compares the destination IP address with its own. If it matches or is a broadcast, the packet is processed. Does not match, then it is discarded. Okay, so a typical structure of IP addresses is divided into two main portions. Okay, we have the network ID portion of an IP address, and then we have the host portion. Now, it's also determined by the class of the IP address that you are using. And I'll explain this in the slides that follow. So you can see on the bottom right-hand corner of the screen, it's a typical example of an IP address. How many octets? 4 octets. Each octet we say is 8 bits. Okay, so a common version, IP version 4 address would be 32 bits in total because each octet represents 8 bits. Okay, there is certain IP addresses that are reserved for the system or for unique purposes. Like if we take the IP address, let me just see if I can draw this. So we have IP address 127.0.0.1. So such an IP address is not assigned to any computer. We call it a local host address, or we call it home or a loopback address. The reason for that is if you type this address on any computer, it's going to loop back to itself. And this is commonly because we find instances where people are developing websites or systems may need to test the website locally. So they need to go on their web browser, and if they type in 127.0.0.1, it's able to run or loop back into their computer and check within a particular directory in that computer for any website files. Okay, so it's for testing purposes only. So bottom line, any computer that's connected to a network must have an IP address and it must be unique. So if we're looking at IP address classes, there are 3 main classes, and we want to focus on these 3 main classes: class A, class B, and class C. Okay, there's also A, B, C, D, and E. Okay, so there's D and E, which D and E is not really flexible in terms of subnetting. Okay, that's why we're going to focus mainly on A, B, and C. Okay, so if you're talking about a class A IP address, what are some of the properties of a class A IP address? Okay, they say value of the first octet is between 1 and 127. So if we look at the IP address on the bottom right-hand side of the screen, you're going to see that the first octet is 192. So this cannot be a class A IP address. Okay? IP addresses beginning at 127 are reserved for loopback. So 127 is out of the picture. You can't assign it to any computer. So basically, for class A, you can assign 1 to 126 in the first octet. Okay? IP address registry assigns the first octet, leaving the last 3 octets to be assigned to hosts intended for large corporate and government networks. Okay, so in a class A IP address, this part of it identifies the network. Okay, the rest of it identifies the hosts. And later on, when you talk about subnetting, I'll tell you the significance of this. Just remember, they say class A is for large corporations, Then we have class B. So again, we can look at the first octet. Okay, so I just heard something there, so I thought maybe you had been kicked out of the meeting or something. Okay, so we have class B. And the value of the first octet is between 128 and 191. By looking at this address, we wouldn't say it's a class B IP address. Okay, so let's see more about its properties. IP registry assigns the first 2 octets, leaving the 3rd and 4th octets to be assigned to hosts. So in a typical network, this part then will be reserved for a class B IP address because the IP registry assigns those letters. Okay, intended for use in medium to large networks. Then we have class C IP addresses. Value of the first octet is between 192 and 223. Okay, the highest number we can have on an octet is 255. Okay, next time I see you, you're going to discuss the binary system, and you're going to see why the highest number you can have per octet is 255. So we say then the range of a class C IP address is between 192 and 223. IP registry assigns the first 3 octets. These networks are limited to 254 hosts per network because 255 is the maximum you can have in an octet, intended for small networks. Okay, so class A IP addresses are intended for large networks, class B for large to medium, or medium to large, then class C intended for small. Why is that so? Okay, so we then talk about the concept of subnetting. Subnetting means we're taking a network, an existing network, and we're creating a smaller network within that network. Okay, a subnet or a subnetwork is a network inside a network. Subnets make networks more efficient. Through subnetting, network traffic can travel a shorter distance without passing through unnecessary routers to reach its destination. So if you have a company and your company has multiple sites, maybe there's a site in Durban, a site in Cape Town, a site in Joburg. Now, what do? Do you buy a new IP address? You should ask yourself the question is, do you buy a new IP address, or simple, you just subnet? You don't have to buy a new IP address for each site. You can buy an IP address once and subnet the other networks, create a network within a network, okay? So we do that through the use of subnet masks, okay? So we are going to be focusing on these 3 classes: class A, class B, and class C. Now, as we went through the earlier slides, we saw that there are certain ranges that define the class of an IP address. But also, by looking at the subnet mask, you can immediately tell what part of the IP address defines the network and what part defines the host and what class IP address it is. For example, if I gave you an IP address and I gave you a subnet mask and I said it's 255.0.0.0.0, you can immediately tell that it's class A, because according to class A definition, only 255, the first octet, is reserved or assigned by the IP registry. The rest are vacant. The rest, or the remaining 3 octets, are vacant. Vacant for who? Vacant for hosts. So we then say a class A IP address is best suitable for larger networks because you can see that only the first octet, okay, the first 8 bits are reserved for the network, which means there are 24 bits at which you can still subnet from to create smaller networks or to create hosts. Okay, so you can see now why this one is best suitable for larger networks. There's more octets. This one is vacant, this one is vacant, this one is vacant, which means you still have more room for inserting more clients there. Okay, and then with the class B, you have IP registry reserves the first 16 bits, which it will take the first 2 octets for the network ID. Then for any host, any dynamically added device, it will have the last 2 octets for itself. Okay, hence we say it basically strikes a balance, and it's suitable for medium to large kind of organizations. And then with the class C IP address, most of the IP address is already taken by the network portion. Okay, it's already taken by the network portion, which means only the last octet can be subnetted to create dynamic hosts. Okay, now I would say that for most companies, a class B would be perfect, a class C would be fine, a really small organization. But think about a ISP, an internet service provider like Telkom. They also purchased their IP address from the top level organization that manages the internet. They also bought their IP address from somewhere. But now, when you are a client or a customer at Telkom, you're gonna subscribe to their services, and they're gonna give you an IP address. So you're gonna get an IP address if you're subscribing to internet, for example. They're gonna give you a router, and the router is gonna be linked to an IP address that is subnetted from Telkom. So already the IP address you're gonna get from Telkom, the first octet will define that this network belongs to Telkom, and maybe you're going to be given, based on the number of customers they have at that particular time, you're going to be given a host portion number in either one of these remaining octets. Okay, so because they're so big, they're large organizations with the need to create smaller networks. Okay, so this is just the concept of subnetting expanded. You're taking a network that is existing, a portion of it, and you're creating another network. So if this was the ISP, okay, they subnet you, and this is your infrastructure at home. So this will be your local area network. So now you are a network within a wider wide area network which belongs to Telkom. So network address translation. Okay, so Telkom subnets you. They give you a router as their customer. So your router will have something that's called a public IP address. Okay, so let's hear what they say about network address translation. They say NAT allows an organization to use private IP addresses all connected to the internet. The NAT process translates a workstation's private address as a packet leaves the corporate network into a valid public IP address. When data returns to the workstation, the address is translated back to the original private address. So how does this work? Okay, so then you are, let's say this is the address. Okay, let's say they gave you this address, the second one. And so assuming Telkom has a class A IP address, it means 198 would already be assigned by the registry. Okay, so you can see they have a large number of customers because this octet has already been assigned, this octet has already been assigned, up to this octet has been assigned. That's the amount of host machines they've already assigned. Each of the remaining octets are already filled with some sort of clients, okay, with some sort of hosts. So let's say you are also one of these hosts and they subnetted you and they gave you this public IP address, which means everybody at home, okay, so now you have internet, everybody's going to connect to the router before they can connect to the internet. And what happens is then that your router also assigns IP addresses to these computers, which means your router makes use of what we call private IP addresses. However, everyone who is browsing or is connected to the internet through this router has the same public IP address exposed on the internet. So if somebody is sitting there on the network doing something illegal somewhere on some sort of website, maybe they're hacking a particular website, and then the web server catches the public IP address of that network. And it's very easy to track the person because then you would look at the class of the IP address, determine who owns it by looking at the network ID portion and say, oh, 198 belongs to Telkom. So this person is a customer of Telkom. And then Telkom just has to look at the host, okay, at the host portion to say, oh, at this particular time, this public IP address was leased by this particular customer. Okay, but then it gets tricky because when they locate the customer's account, they won't be able to tell who exactly in the household was the one who was doing something illegal, unless they dig deeper using a different type of address called a MAC address. They won't be able to pick that up purely by using private IP addresses. Okay, because number one, private IP addresses are not tracked by the web servers on the internet. They are private. Only the router knows. Also, private IP addresses are leased, so they change. So one time this computer would be 10.0.0.1, then the next time is 10.0.0.2. Okay, so they differ and change often. So we're going to talk about later on the use of these private IP addresses and how DHCP actually helps to assign them. So common email protocols, you may have seen this somewhere when you are asked to configure email settings on a phone or wherever you needed to configure, or Outlook, you need to play around with these protocols, okay? So post office protocol is a protocol that is used for downloading email, okay? Receiving, the post office, you receive things. IMAP is another protocol for receiving. The difference is that with IMAP, it says it's used to manage email messages locally, yet stores them on the server. Okay. With post office, is used to download incoming messages from an email email servers to local desktops. Okay, so this one IMAP downloads a copy of it locally onto your computer. POP3 rather downloads a copy of it onto your local computer. So the changes are not really synchronized fully when you delete. Okay, so with IMAP, however, you are actually you're basically like a terminal. Okay, so everything still resides. You can access the messages locally, but everything is stored on the server. It's not downloaded locally onto your phone, for example. Okay, so SMTP is the only protocol for sending that exists, for sending emails. So when you asked SMTP or POP3 settings, you gotta know the difference between the two on your phone. So then we have a protocol called Dynamic Host Control Protocol. Okay, and this protocol is used to dynamically assign IP addresses to new computers on the network. You can imagine an organization with a very big network and so many users, and people are bringing their computers, they're connecting to the Wi-Fi, people are bringing their cell phones, they're connecting to the Wi-Fi. The network administrator without DHCP will have such a headache because they would have to manually assign these IP addresses to these hosts before they can communicate. But thanks to DHCP, for as long as you have the password for the network or you're connecting using a cable, automatically the DHCP protocol will assign a IP address based on the available number of available host spaces. Okay. So we also have the domain name system. Okay, so DNS is a name address resolution protocol that keeps a list of computers' names and their IP addresses. With DNS, a user can use a computer's name instead of IP addresses. So when the internet started to kick off, they realized that remembering IP addresses is very tricky because there's bound to be a lot of internet services that are going to exist in the future. So that's how DNS came about. So it helps us to use names instead of IP addresses, like how you see on a cell phone's phone book. Okay, we search for people using their first name and last name, and it gives us their cell phone number. If we just had to remember all their cell phone numbers, you're going to get confused. Okay, so DNS is basically a protocol that does that. It maps a IP address to a human readable name. Okay, and we say that domains typically have multiple levels. At the top level is the extension. For .com, .commercial organizations, okay? .org, organizations, right? .edu, educational institutions, government extension. So top level is the highest level, okay? You can have in a domain and it's defined by either these extensions, domain extensions. There's also .co.za for companies located in South Africa. Then we have the second level. This is usually the name of the company or the name of the organization. So we say something like Microsoft.com. Okay, so the name is at the second level, the name of the organization. And then at the subdomain level. Okay, so subdomains are basically subfolders within the web server, and they are given also domain extensions. So something like books.microsoft.com could be a full domain, where the books is a subdomain to say we are looking within the books folder of this computer. Okay, the common root or host level extension you'll see is this one, the World Wide Web. So if you're not using any subdomain, you can type www.microsoft.com, and it's going to send you to Microsoft website because it points to the root. Okay, www points to the root level. However, when you start to use a subdomain like books, software, then you are referencing a specific folder. So DNS, in simple terms, it's a protocol that resolves IP address to the relevant domain name. So MAC addresses, okay, also called physical addresses, are located or assigned to a computer's network interface card. So any computer that has network capabilities, whether wired or wireless, will come with the MAC address card. Usually it's written, you see it's written on the hardware itself. So when you open up the computer, you can see the MAC address. MAC address, that's why we call them physical addresses, do not change and they are not leased. Unlike IP addresses, which are can change, and the only thing they have in common is that they are both unique. So you can see that in a typical TCP/IP communication, MAC addresses are very useful because when a message is sent, it is sent along with the destination's MAC address, okay, the source's MAC address, the destination's IP, and the source's IP. That ensures that when the message or the data reaches the other end, it is assembled properly because it's chopped up into packets, okay? And there could also be multiple computers on the network. So it needs to make sure that it really is going to the correct destination and we can really reassemble it in the destination machine. So MAC addresses, very useful physical addresses. Earlier on, we talked about how would you be able to pick out who did something wrong. And for the mere fact that, you know, maybe computer A in the household belongs to someone, computer 1, sorry, belongs to someone, and then computer 2 maybe belongs to someone else, then we can pick out that, okay, this is the MAC address of the computer that was doing something illegal in our network. So this is the person that you must arrest. Don't arrest everybody in the house because the public IP address was exposed when one person in the network was doing something illegal. Okay, so ports as well. Ports are very useful. You can't talk about protocols without talking about ports. Okay, so certain protocols are so important that they have their own ports reserved. Okay, so we're not talking about here like physical ports like USB ports and so forth, although the concept is the same. So a port is an interface at which something enters something else. Okay, so if we're looking at it from a person entering a home, they would go through the door. So the door is something like a port. Okay, and so we can look at, I tend to compare this whole thing like this whole communication, network communication, as looking at it as a building. Okay, a building and a protocol, you can look at it as a company exhibiting a particular flow number. Okay, so no two companies can operate on the same flow. Under normal circumstances, it doesn't happen. So if you're looking at a building, the 20th floor is reserved for FTP. That's the company that's operating there. And this company also takes floor 21. Okay, so certain protocols can take more than one port. So then we have the company SMTP is taking port 25. We have the company HTTP is taking port 80. Okay, so it's basically the interface at which this data enters the network. So the OSI model then is divided into layers, and these layers are the physical layer, which is layer number 1, the data link layer is layer number 2, the network layer number 3. Then we have the transport, and we have session, and we have presentation, we have application in that order. And so in total, it's 7 layers, okay? And the data, when it's being sent by the sender to the receiver, it goes through these 7 layers, okay? So if the data is going from sender to receiver, okay, then the sequence goes from layer 1 to layer 7. Okay, if the data is going from this side to that side, then it goes from layer 7 to layer 1, and I'll tell you what that means in the slide that follows. So again, looking at this being 1 and this being layer 7 all the way up. So the application layer, we have all of these applications that end users sit in front of when they do their work. Outlook, Gmail, all of those operate at the application layer because they make use of these protocols, okay? Office 365, HTTP, SMTP, Gmail, sending email, downloading files, whatever. So we have these applications that we're sitting in front of, and we are clicking buttons. So we are interacting with the computer, or we're sending an email. Example of sending an email is sending data from one computer to another. So if you are using SMTP or application for sending email, it means the sequence will be from 7, okay, to 6, to 5, to 4, to 3, to 2, to 1. Because you are what? You are the sender and you're sitting in front of an application. But if you are the receiver, it means the sequence will then go from here to here, to here, to here, to here. Okay, so I'm hoping that that makes a bit of sense, that this sequence is reversed based on whether you are sending or you are receiving, but at the end of the day, the data will still go through these different layers. Okay, so what do these layers mean? The physical layer, we find the network interface card. Okay, we find the network interface card operating here. Our Ethernet cables, all our cabling operates here. Then we have the data link layer, which data is then converted for the higher layers. Okay, remember that data is in 1 and zeros, so then it needs to be converted into bytes for the layers above. Okay, then we have the network layer, which then IP addresses, the internet protocol or IP addresses is assigned to the packet. So information about the network that is sending, information about the network that is receiving is assigned. Then we have the transport layer, where the vehicle which the data is going to be sent through is defined. Is it going to be TCP or is it going to be UDP? Okay, the session, these are the presentation and session really are not associated with TCP IP communication, but nonetheless they're present as part of the larger OSI model. So session layer, what does it do? It creates or terminates sessions, okay? But there are no specific protocols operating here. Then we have the presentation, which ensures that the data is in a proper format for display in the application. So if this is a web-based application, then the presentation layer will format that data into HTML tags and so forth. Okay. So then we have all of these well-known hardware devices on a network. We have hubs, which basically extend the amount of connections or ports we can have on a network. We have routers, and then we have a switch, okay? The router being the most sophisticated network device that exists. The hub is just an extension port. The switch, similar to the hub, but with additional mechanisms for transmitting data and managing collisions of data. Now, the reason why this slide is included here is just to show you that the hub is an example of a device that will operate at layer 1 of the OSI model. Why is that so? Because the hub is just a physical interface. It brings us ports, and for connecting these cables, it's just a physical thing. There's nothing more to it in terms of the way it operates. However, the switch, okay, since the switch manages data, it's going to be operating at layer 2. Okay, it manages data, how the format the data is in, how the data is transmitted to avoid collisions. Layer 3, we would find that the network layer, the router. Why is the router at network layer 3? Because the router has DHCP and DNS, and the router will be assigning IP addresses. As you can see, IP addresses are assigned at the network layer. So we say that the router is a device that operates here at this particular. These other protocols are doing the same thing as IP, but they are specific to certain platforms. So we're focusing specifically on IP because IP is standard. No matter if you're on Linux, Windows, or whatever, it's standard. Okay. So moving on to IEEE 802 networking standards. Describes how network interface cards can access and transfer data across a variety of networking media and what's involving in attaching these devices to a network. So we have these logical link controller sublayer and the media access control layer, okay, or the MAC address, okay? So this is the physical layer or the physical address assigned to the card. Then you also have logical link sublayer, controls data link communication and defines the use of logical interface points used to communicate to the upper OSI layers. Okay, so this is the one that's in charge of actually translating the actual data. This one assigns a physical number to the data being communicated, and this all happens at layer 2, the data link layer. So there are a set of these standards. Some of them have been disbanded, some of them are still being widely used. Okay, we have Ethernet LAN, which is 802.3 standards. Okay, so very popular Ethernet cables. We still see them. They're still in use today. We still see them. Okay, we have, although there's a new version of fiber optic cabling, but before the earlier version is fiber optic technical advisory group standards, which is 802.8. Okay. Which other one is commonly used today? Let me see in this list. Is this the same? Okay, so this is duplicated, but the Ethernet standards, other ones we may have talked about them in terms of networking because they are there in the history of networking, like token bus, token ring, metropolitan area networks, but how often do you actually see those things in existence today? Okay, but we can agree that with 802.3 standards, and I'm sure there's another set. I think I left out a particular, may have duplicated this by mistake, but I was looking for the wireless LAN set of standards. But either way, the important thing to take out of this is that IEEE 802 sets of standards define how what mediums are used to transmit data through a network. Okay, it can either be through wireless means or wired means. Okay, and if you're talking about using wired connections, Ethernet is one popular example, which is 802.3. Okay, so in conclusion or in summary, this presentation we covered TCP/IP, and it said it's the principal protocol used in computer networks. You also said that the transport layer provides reliability and works with segment by segmenting data. The application layer consists of protocols such as HTTP and DNS and SMTP with the other wide variety of application protocols. And we also said that the OSI reference model and IEEE Project 802 define a frame of reference for networking and specify the operation of most networking technologies in current use. The OSI reference model separates networking into 7 layers, each with its own purpose and activities. Okay, so that is the 6th study unit merged with some key concepts from the 5th study unit. Okay, so Sinisha, is there any questions that you may have pertaining to these study units?